Hi, my name is Isaac Gerg, and I'm a PhD student at Penn State University in the United States. I'm part of the Information Processing and Algorithms Laboratory under the supervision of Dr. Vishal Monga. Today, I will be presenting on real-time Deep Synthetic Aperture Sonar, or SAS, autofocus. Let's begin by looking at an example SAS image that has been defocused. On the left is our defocused SAS image that is a result of the image reconstruction process. On the right is the ideal, well-focused version of this image. I want to highlight two areas here. The upper arrow shows a point scatterer which has been blurred due to defocusing. We know this by the smearing in the along track direction as the vehicle traveled in this direction during collection. We see in the right image that the point scatterer is well formed and focused. The second area I want to highlight is the lower arrow, which shows seafloor texture that is diminished due to defocusing. We see on the right image that this texture is a bit more pronounced when the image is well focused. So what are the sources of imaging defocusing? Well, you can think about the synthetic aperture sonar as integrating time series over multiple transmissions or pings for a pixel of interest on the seafloor. Image defocusing results from misestimating the time of flight of the transmitted waveform from the transmitter to the seafloor and from the seafloor back to the receive array. Any time of flight misestimation along this path will result in image defocusing. Two common sources of error in this process are 1. Vehicle position error, meaning my estimation of where the transmitter and receivers are is incorrect, and 2. Sound speed error, meaning my estimation of the speed of sound in the water is incorrect. So the inspiration of our proposed autofocus method comes from Cook et al. From a JOE paper that they published in 2008. In this paper, they observed that humans have very little issue in telling focused and defocused imagery apart. Furthermore, they observed that humans can examine a defocused image and in many cases tell what the source of the blur results from, whether this be speed of sound error, which results in quadratic phase error, or high frequency phase errors such as vehicle yaw error. What we thought was, could we use a convolutional neural network, or CNN, to identify and estimate the phase aperture error in a SAS image and then automatically correct it? So let's take a quick look at the mathematics of this problem in the vein of traditional autofocus methods. Let's assume you are given a blurry image, little g sub e, and the associated phase aperture error estimate which the blur results from. We will call this phi hat. To focus the image, I take the Fourier transform of the input image, which gives me phase and magnitude maps in the k-space. Next, I apply the phase correction along the ky axis, which gives me a new phase map. I then carry over the magnitude map and then inverse Fourier transform to arrive at the autofocused image. This process is described by this equation, where this operator functions like the broadcast operator, and this operator is a pointwise multiplication. We compose this process as an optimization scheme by which we are given g sub e and we want to estimate phi. We do this by solving this optimization problem, assuming that the focused image is sharp or has high contrast, so we use a metric m to measure that. We then optimize this for phi hat and then apply it as the phase correction in the manner we just described. Historically, there's a few metrics which have been often used to optimize image sharpness or contrast. They have been used for both optical imagery and synthetic aperture processing. In a typical use case, these metrics are iteratively optimized on a per image basis by ingesting a single look complex, or SLC image, which contains complex pixels. Next, a candidate phase correction is estimated, and then the metric is computed on the resultant magnitude image. The process then repeats. We found that there are 4 common metrics often used in the literature. FINUP, sum of squared intensity, Steve Fortune's mean normalized standard deviation, which was used for SAS autofocus incidentally, Schultz's optimal sharpness function, and minimum entropy, which we see lots of uses as a prior in the optimization of many image and signal processing problems. On this slide, I describe the mathematics of the metrics I mentioned on the previous slide, but I talk a little bit about how they're used in practice. So recall our optimization problem. Using one of the metrics on the previous slide, a common method is to use gradient descent or Newton's method to autofocus a given input image. However, practitioners often find that these metrics can fall into bad optima whereby the optimization procedure doesn't converge or it takes a long time to converge. In an attempt to fix this problem, often a weighting function, which we denote as W, is applied to the autofocused output before the metric is computed, with the idea that this weighting function gets rid of bad areas of the image, such as those areas with low contrast. Overall, the metric-based methods suffer from two practical problems when deployed on real systems. One, they may have convergence issues, resulting in no autofocus taking place, and two, they require dozens of iterations, which prevents their real-time use on low size, weight, and power systems. The method we propose, which we call Deep Autofocus, extends the metric-based optimization model we just showed in two ways. One, we extend the form of the weighting function W so that it is implicitly learned from a set of training images. In this way, each image is no longer autofocused independently. You can think of it as what is learned by autofocusing one image can be leveraged to autofocus another image. And two, we reformulate the optimization problem so that the compute burden is shifted to the training procedure, and during test time, only a single iteration or function call is needed to autofocus each image. So now I will show our proposed deep autofocus network and how we train it. We begin with a single look complex image in real and imaginary format. We then transform this image into a dynamic range compressed version of itself and also compute the phase of each pixel. We then pass these maps into a pre-trained densenet, which serves as a feature extractor, and it's followed by a regression network composed of a global average pooling module and a multi-layer perceptron. The output of the regression network is the model parameters of our phase error. Our phase error model is parametric and modeled by a 10-degree polynomial. So the output of the MLP are the coefficients of this polynomial. Those coefficients are fed to the phase model, which creates the phase error estimate to apply across the aperture. This is now our phi hat. Next, we apply the phase correction in the Fourier domain, which we can do in our deep network since the Fourier transform is differentiable. We then inverse Fourier transform to the spatial domain to arrive at our autofocused image. Next, we prepare to compute our loss function, which we optimize during our network training. And we do this by measuring the image sharpness of the input image and the autofocused image. We then compute the loss function, which is a relative sharpness improvement loss that we define here. This loss seeks to make the autofocused image G hat sharper than the input image G sub E. The loss is then backpropagated through the network and the weights are updated. What is nice about this algorithm is that during training, I compute this loop many times over all the training data, but during test time or inference, I only have to compute the forward path once, which is shown here in these red arrows. This makes the algorithm very fast to deploy in a real system. To test the efficacy of our algorithm, we create a set of artificial low-frequency phase corrupted images from pristine beamform images, and we autofocus them using deep autofocus and the four traditional metrics that I previously mentioned. We will compare the image quality of the autofocused images to ground truth. To train our deep autofocus network, we start with a pool of roughly 500 high-frequency SAS images. We select a random 120 images to serve as our training set. We perform data augmentation on this set by artificially corrupting each image with a random phase error, which is based on our parametric polynomial model. We select a polynomial of random degree and random coefficients, and then randomly scale that resulting function in a way so that its maximum absolute value is no greater than 18 radians. For the validation set, we randomly select another set of 120 images and apply the augmentation strategy just described, but only once to the image set. Finally, for testing, we select the remaining 264 images from the dataset and also corrupt them once using the same strategy used in augmentation, but again, only once. We train our network using stochastic gradient descent for 10,000 iterations. For testing, we simply choose the model with the best validation set performance. For the comparison methods, each metric is implemented on a GPU and trained for 10 iterations using gradient descent. We think 10 iterations is conservative, as in practice, you may optimize for several dozen iterations. One free parameter has to be selected, though, for each method, and that's the learning rate of the gradient descent. We ran each method over a wide range of learning rates and report the performance of the run, which gave us the best results. We compare all of the methods against two commonly used image metrics, peak signal-to-noise ratio, or PSNR, and multi-scale structural similarity, or MS-SSIM. We compute these metrics between the autofocused image and the associated ground truth image. We use PSNR as a metric because it has a long history of use and folks are quite familiar with it. However, its result does not always correlate well with human quality assessment. So, we use multi-scale structural similarity as another evaluation metric because this metric was designed to correlate well with human-assessed image quality. Our results show us two interesting things. One, deep autofocus does, on average, a better job of autofocusing the images than the comparison methods. Two, looking at the left tails of the violin plots, we can see that deep autofocus doesn't catastrophically fail like the comparison methods. These kinds of catastrophic failures are often what give practitioner headaches when trying to deploy these algorithms on real-time systems. Next, we compare the runtime of all the methods. Recall that all the methods are implemented on a GPU and on the same GPU. We let the metric-based methods run for 10 iterations, while we only run deep autofocus for a single iteration. We can see that deep autofocus is at least an order of magnitude faster than the comparison methods. To conclude, we introduce a method, which we call deep autofocus, which can autofocus low-frequency phase errors and high-frequency SAS imagery in a robust fashion and in real time. Our formulation extends the traditional metric-based optimization approach in two ways. The first, we extend the form of the weighting function W so that it's learned over a set of images. And two, the compute burden of the autofocus task is shifted to training time so that during deployment, only a single iteration of the algorithm needs to be run. We notice that deep autofocus produces imagery that is better than the comparison methods by a considerable margin. When examining the PSNR and MS-SSIM distributions of the test set, we can see that the deep autofocus doesn't catastrophically fail like the comparison methods. I show an example on the right of this situation. We can see that our image under test is defocused, and the results using SSI are also defocused. However, deep autofocus is able to focus the image to look much more like the ground truth. We notice the same behavior for all the other comparison methods on this image. Finally, the runtime of deep autofocus is at least one order of magnitude faster than the comparison methods. So with that, I conclude and I thank you for your time, and I will take any questions you have.